In the heart of a bustling city, under the flickering neon lights, I found myself walking past an old clock tower. The hands seemed to dance in a mesmerizing pattern that made me think about time itself. But what if our understanding of this fundamental concept was just the tip of the iceberg? What if there were more dimensions and connections hidden beneath the surface? That's where quantum entanglement comes into play, a phenomenon so strange. It defies common sense yet is backed by solid evidence in scientific labs around the world. Imagine two particles that are connected in such a way that they can affect each other instantaneously, no matter how far apart they are. It's like having twins who can communicate without even speaking. In 1935, Albert Einstein famously referred to this as spooky action at a distance. He couldn't believe it was real because his theory of relativity suggested that nothing could travel faster than the speed of light. Yet quantum entanglement seemed to break this rule, hinting at an underlying structure of reality we haven't yet fully grasped. Let's zoom out for a moment and imagine you're holding two marbles in your hands. If these marbles were entangled, when you drop one marble on the floor, the other would know instantly where it landed. This is not just science fiction, this bizarre behavior has been observed countless times by scientists using photons of light instead of marbles. But why does quantum entanglement work? And how can we reconcile such a phenomenon with our everyday experiences and classical physics theories? Let's take a step back to the early 20th century. At that time, physicists were grappling with new ideas about atoms and subatomic particles. Niels Bohr and Werner Heisenberg introduced concepts like wave-particle duality and uncertainty principles, which challenged everything we thought we knew. Then came Einstein, Podolsky, and Rosen, EPR, in 1935. They proposed in the heart of the universe, there lies a mystery so profound that it challenges our very understanding of reality. The concept of quantum entanglement has captivated minds for decades, much like an unsolved puzzle waiting to be unraveled. Imagine this, two particles are created at the same moment in time and space, but they end up on opposite sides of the galaxy. Despite being separated by vast distances, one particle instantly affects the other's state, no matter how far apart they may be. It's as if their connection transcends both space and time. Scientists have been trying to understand this phenomenon for over a century now. In 1935, Albert Einstein himself was deeply skeptical of quantum entanglement, famously referring to it as a spooky action at a distance. He couldn't reconcile how particles could communicate with each other so quickly without any medium or signal traveling between them. Quantum mechanics has always been a strange and counterintuitive field. It deals in probabilities and wave functions that seem to dance around the very fabric of existence. But entanglement takes this strangeness to an entirely new level, defying our classical intuitions about how things should work. In recent years, experiments have shown that quantum entanglement is not just a theoretical curiosity but a real-world phenomenon with practical applications. For instance, it's being used in the development of ultra-secure communication systems and even in advanced cryptography methods like quantum key distribution. But despite all this, we still don't fully understand how or why it works. The question lingers, what is happening at the most fundamental level? How can particles be connected across vast distances without any physical interaction? Scientists have proposed various theories to explain entanglement, but none of them are widely accepted as a definitive answer. Some believe in hidden variables that we haven't yet discovered or observed. Others suggest modifications to general relativity might provide insights into this phenomenon. The story doesn't end there, it's just beginning. In the heart of a bustling city, under the flickering neon lights of late-night street lamps, we find ourselves pondering one of nature's most perplexing puzzles. Quantum entanglement is like a whispered secret between two particles, a silent pact that defies the very fabric of space and time. Imagine you have a pair of magical dice. No matter how far apart they are thrown into different corners of the universe, when one lands on 6, the other always matches. It's as if there's an unbreakable bond between them. This concept might seem straight out of science fiction, but it's real and has been proven by countless experiments. The story of quantum entanglement begins in 1935 with a letter from Albert Einstein to his colleague, Boris Podolsky. In this correspondence, Einstein posed the question, can something be in two places at once? He was skeptical about the implications of these strange findings and named it spooky action at a distance. Despite his reservations, quantum entanglement has since become one of the most fascinating areas of modern physics. Today, we find ourselves standing on the threshold of this enigma. We know that particles can be connected in such a way that what happens to one instantly affects the other, no matter how far apart they are. But why does it work? How can these tiny specks of energy maintain their mysterious connection over vast distances? One day, as we explore the depths of this mystery, let's imagine ourselves holding two particles, particle A and particle B. As soon as you separate them by a great distance, say, across an entire galaxy, their properties become intertwined. If particle A is observed to spin clockwise, particle B instantly spins counterclockwise. This phenomenon works even if they are light years apart. The key lies in the wave function of these particles. In quantum mechanics, everything exists as probabilities until it's measured or observed. When two particles interact and entangle, their individual in the heart of the quantum realm lies a mystery that defies both logic and imagination. Imagine two particles so intimately connected that no matter how far apart they travel in space or time, whether from one end of our galaxy to another, they can instantaneously affect each other's state, as if sharing an invisible thread. This phenomenon is known as quantum entanglement. Scientists have been wrestling with this concept for decades, trying to understand why it works and what implications it might hold. The more they explore, the more questions arise, questions that challenge our very understanding of reality itself. Let's begin by diving into a story from history. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen posed this question in their famous EPR paradox paper. They proposed an experiment where two particles are created simultaneously and separated so far apart that classical physics would predict no connection between them. Yet, quantum mechanics predicts they will still be entangled. Einstein famously called it spooky action at a distance. He couldn't wrap his mind around the idea of instantaneous communication without any medium or signal traveling faster than light. His skepticism was rooted in a belief that nature should not rely on such mysterious mechanisms to function. But here's where things get intriguing. Experiments started pouring in, and one by one, they confirmed quantum entanglement. A famous experiment conducted at the University of Innsbruck demonstrated this phenomenon with high precision. Using two photons separated by just 10 meters, though the implications were clear even then, if it works over such a small distance, imagine what happens when we increase that separation to astronomical scales. The challenge lies in understanding how these particles maintain their connection. Is there an underlying mechanism at play, or is this truly spooky action? Some scientists argue for hidden variables, the idea that entangled particles still have some local interaction unseen by current technology. Others believe the concept of locality itself needs a radical rethink. Perhaps space and time are not as absolute in the world we live in. There are some mysteries that seem almost too strange to be true. The phenomenon of quantum entanglement is one such mystery. It's a concept so bizarre it challenges our very understanding of reality. Imagine this: you have two particles that were once connected and then separated by vast distances. What happens if something changes with one particle? Astonishingly, the other particle responds as well, instantaneously. This seemingly impossible connection between entangled particles is what quantum entanglement is all about. Why does it work? Scientists can't explain this entirely yet, but they have a few theories and experiments to support their hypotheses. For instance, consider Bell's theorem, which suggests that no theory based on classical physics could account for the results of certain experiments involving entangled particles. It was as if these particles were communicating with each other faster than light allows. In practical terms, this means we can use quantum entanglement to create something called a quantum network. This would be a network where information is transferred instantaneously between points, potentially revolutionizing communication technology. Imagine the implications for global communications: no lag time, no delays, just real-time interaction across distances that are light years apart. But let's think about it from another angle: cryptography and security. Quantum entanglement could provide an unbreakable encryption method because any attempt to measure or observe a particle will instantaneously affect its partner in the network. This would make hacking nearly impossible, offering a new frontier for secure communication. On a more philosophical level, quantum entanglement challenges our notions of causality and locality. It suggests that perhaps everything is connected on some fundamental level, no matter how far apart they are. This has implications not just in physics but also in metaphysics, questions about the nature of reality itself. Moreover, this phenomenon could have profound effects on computing technology. Quantum computers use entangled particles to process information in ways classical computers can't match. By harnessing quantum as the stars twinkle in their celestial dance across the night sky, ponder for a moment. Quantum entanglement is one of those enigmatic phenomena that defy our everyday understanding of reality. While it might seem like something out of science fiction, teleportation and instantaneous communication, quantum mechanics has shown us that these ideas are more than just figments of imagination. Imagine two particles, entangled in a way that no matter how far apart they travel through the universe, changes to one particle can instantaneously affect its twin. This concept alone challenges our classical notions of space and time, making it almost impossible for our intuition to wrap itself around fully. The mystery lies not just in understanding quantum mechanics but also in grasping why this works. Despite decades of research, we still don't have a complete theory that unifies the laws of general relativity with those of quantum physics. These two theories describe different realms. One deals with gravity and large-scale phenomena like planets and stars, while the other governs the world at microscopic scales. Yet when you bring these two worlds together in an entangled system, something magical happens. The particles behave as if they are connected by some invisible thread, a connection that defies conventional explanations of causality. This raises a host of philosophical questions. Is information being transmitted faster than light? Or is our understanding of cause and effect fundamentally flawed? Theoretical physicist John Bell once said, "If you think about quantum mechanics without getting dizzy, then you haven't really understood it." And there's truth in his words. The very nature of entanglement challenges us to question the fabric of reality itself. Consider this: in a world where particles can be simultaneously here and not here, wave functions collapse upon measurement, and probabilities become our only certainty. How do we reconcile these concepts with our everyday experiences? Is there an underlying order that governs all of nature's complexity, or are we just observing patterns in a chaotic soup? The quest for answers continues. Researchers like Not All Mysteries have answers, but we keep searching. Subscribe to join the hunt.